In our previous classes, we have talked about public key crypto systems, and mostly we have seen two different public key crypto systems, namely RSA public key crypto system as well as ILGAMAL public key crypto system. In both of these two schemes, we have already seen that we need big primes. So how big are they? So they should be reasonably big, like maybe of this order. So it contains 904 digits. So natural question that comes to our mind is, are they really primes? I mean, here this is one example. Is it really a prime because the last digit is only odd? So you, since this last digit is 9, you can never be sure that this is prime or not. But suddenly this is not even. But till now, whatever we teach you, it's not possible for you to check, even with your machine, to check whether this is a prime number or not. So in today's class, I will basically try to get some of the important tools that will be used for primality testing, especially to get these big primes. And there are many ways to do so, but one of the very simplest way to do so is by using some very easy number theoretic technique, which are highly based on abstract algebra, and that is known as quadratic reciprocity. So if you just have a look at, if I ask you to check whether a number is prime or not, certainly the best algorithm that you know till now may be of this form. So maybe you start with n, and then you check whether from start with 2, and you go for sometimes maybe n minus 1. So starting from 2, 3, and dot dot n minus 1, and check whether any of this I, whether it divides n or not. If any of the i's divide n, then your conclusion will be the number is not prime. But if none of this from 2 to n minus 1, if none of them will divide n, then your conclusion will be the number is prime. So one may suddenly say that I could have a better algorithm, in that sense that I may go from 2 to n by 2. Instead of n minus 2, I may go to n by 2. And you can also check whether any of these i's will divide n or not. If some of them will divide n, then certainly your conclusion will be the number is not prime. But if none of the 2 to n by 2 will divide n, then your conclusion will be the number is prime. But one may again make it a little more efficient, in the sense that one may go to say 1, 2, so 2 to 3, and then not n by 2, but instead he or she may go till square root of n. And then also, if the same thing happens, that means if some of the i's will divide n, your conclusion will be the number is not prime. If none of them will divide n, then your conclusion will be the number is prime. So in that way, you may see if n is of this form, say 1, 0, 0, 0, 0, and if you do the first algorithm, like from I equal to say 2 to n minus 1, then around you have to do with around 10,000. So maybe 9999, 4 nines, or maybe this is 10,000. So you may have to do it for maybe around of this number of steps you have to calculate. But if you take the second option, for example, I equal to 2 to n by 2, then you may have to go like up to maybe uh, this 5,000 many steps. So from around 10,000 step to you have made it half. But if you take the last option, I equal to 2 to square root of n, then you may find that it may be of 100 steps. So it's basically, you can now see that from around 10,000 or 5,000, whereas you'll be able to say the result by using maybe 100 steps. So it's quite a significant improvement of your result among 1 to 3. But If you are going to use it, for example, suppose my number is of this big long, and then if you take the square root of this, then also the number of digits will be around 450. So this is still a huge number, maybe of this size. So if you consider 450, maybe of around half. So this big number, and if you consider this from I equal to 2 to square root of n, that means half of this number around, then also you'll be surprised to know that the supercomputer will also be not able to do that within, say, maybe it may take around 100 years for a supercomputer to check whether the number is prime or not. So that is not feasible. Okay, so we need something extra that will give me the result very quickly. And as I mentioned, as I have shown you in my last class, that this is indeed possible, and I get it this big prime by using my small laptop, by using a small code in Sage programming language, which is very useful in our computing things with big numbers. Whereas if we consider C programming language, no doubt that C programming language is much faster than Sage programming language, but still to achieve, to get this big prime in C programming, you will have to do a lot of things. Whereas in Sage programming language, which essentially consists of C, or you can say Python and C, which gives us a more efficient way, not in efficient in the sense that it gives us within less time, but surely you don't have to code much. In that way, it's efficient because you don't have to code much. Everything is already inbuilt within Sage. So only a one line code will give you the answer. But to get it, okay, so to get it, whereas if you want to do it in C programming language, maybe the answer that you will get maybe in a, I mean, it would be a quicker time because C programming is much more efficient. But suddenly you have to and suddenly that will take a lot of your effort. But once you do that, then you will be certainly master in C programming. Okay. But for the sake of simplicity, we can use directly Sage programming language, and by using Sage programming language, you can certainly get this big primes very easily. That I have already shown in my last class. Okay. So the question is how the Sage programming language, or how, what are the logics that this programming language they use to get this big prime. So one of the reasons for this class is basically to have a basic idea for that, and to do so, let us first have some prerequisite for that. So the basic topic for today's talk is basically quadratic reciprocity. So the law of quadratic reciprocity or quadratic residues. Okay, to understand that, let us first start with a very simple thing. Suppose I am giving you some, say some positive integer. Say a is some positive integer, say positive real number. And if I ask you the question, can you find the square root of a? That means, suppose I am giving you, say 9, a equal to 9, and ask you the question, can you find square root of 9? What would be your answer? You will certainly get the square root of 9. So that is certainly plus minus 3. Okay. But if I give you, say, a equal to 7, and if I ask you the same question, can you find the square root of 7 as a positive real number, as a real number? So you will certainly say that, okay, any positive real number must have a square root, and you know that there are exactly two square roots, that is plus minus root of 7, and that number is suddenly a real number. But if I ask you the same question, can you find the square root of 7 in integer? That means I want to check whether this equation holds in integer, whether this equation has a solution in integer, in Z. Similar question I could have here also, whether this equation has a solution in Z. So you can see that if I consider instead of Z, if I have R here, if I have R here, then suddenly both the questions will have the same answer. Yes, there will be. But if I replace it by R by Z, then suddenly your answer will sometimes be yes and sometimes be no. For example, here you will have yes answer that will have integer solutions, and that is nothing but plus minus 3. But here you will have the no answer because there exists no integer solution for the equation x squared equal to 7. Okay. So that means there are some integers whose integer square root exists, and there are some integers whose integer square root does not exist. So now if I change the same thing by from Z R, from here, say I change it to ZP for some prime. For example, suppose I have taken, say, P equal to 11. I consider Z11 star. So now you know what is Z11 star. That means U11. And if I ask you, take some element, say class A belongs to Z11 star, and if I ask you the same question, whether x square congruent to class A exists in Z11 star or not. That means whether you have some class X whose square will be class A. Okay, so if I ask you the question, then what do you think that your answer will always be exist? For example, if I consider this in my last, I have first considered with R, then I consider with Z. So all of them are ring. Now I have replaced it by, say, Z11 star. So I know that that has also some algebraic structure. So the same question, whether this equation will have some solution in Z11 star. What will be your answer? Any guess or any answer that you want to share? Any answer? What would be your answer? Anybody? Okay, so let us have a look. So let us try to see all elements in Z11 star. So let's start with 1 square. Since I have taken Z11 star, so 0 is not here. You can understand it. So let's start with 1 square. Then this is 1. If I consider 2 square, then this is 4. If I consider 3 square, then it is 9. If I consider 4 square, it is 16. 16 in Z11 is how much? 16 in Z11 is
5.
5. If I consider 5 square, then how much it is? 25. 25 in Z11 is how much?
3.
3. Now if I consider 6 square, what is the value of 6 square?
36.
36 in 11. Z modulo 11 how much? In modulo 11 how much? 36. Again class 3, right? If I consider class 7 square, what would be the value? 49. 49 means 44 plus 5, that means class 5. So 7 square. Now you can understand. So this is 8 square, this is 9 square, and this is 10 square. So it has a nice structure. So if I take this element, see, I have exhausted all the elements of Z11 star. I have exhausted all the elements, and I found that if I consider these elements, for example, if I consider A to be class 1, then suddenly the square root of A exists. What are the square roots of class 1? Can somebody tell me? What are the square roots of class 1?
Sir, class
So
10 and
10.
class 1.
Exactly. So if I consider A to be class 1, then certainly you find that this is the square root. So if you consider, if I just deviate the notation, if I misuse this, nobody writes in this way. So if you consider this, then what you will get? So this is, sorry, not this way. I should write in that way. So square root of class A is nothing but square root of A means 1 square, also square root of n square, right? And this is nothing but class 1, and also, so it should not be, I should put it comma here, because class 1 and class 10, they are not exactly the same, but class 10 also. Okay, so that's why you can understand that uh, square root of class 1 exists, and the square root of class 1 is class 1 as well as class 10. Similarly, square root of class 4 also exists, square root of class 9 exists, square root of class 5 exists, square root of class 3 exists. Okay. Now, if I ask you what would be the square root of class 6, what will be the square root of class 6? What will be the square root of class 6?
Sir, it will not exist in Z star 11.
Exactly. So you can see that I have exhausted all the elements whose square root exist, right? There exist no other elements whose square root exist. And so if I write it in this way, like if I write it in this way, then there will be a kind of simple list, and you can find that in that list everything exhausts. Like the square root exists. So if I write square root exists for class 1, class 4, class 9, class 5, and class 3. So square root does not exist for class 2, class 6, class 7, class 8, and class 10. So in Z11 star, you see that there exist exactly 10 elements. So class 1 to class 10, 10 elements, out of which exactly 5 elements are there whose square root exists. Whereas exactly 5 elements are there whose square root does not exist. So now you may think that, okay, that may be a coincidence that exactly the same number of square roots and same number of non-square roots. So there are some technical names corresponding to that. These elements are called quadratic residues. So these elements whose square root exists are known as quadratic residues. Quadratic residues. Residues. And these elements are called non-quadratic residues. Non-quadratic residues. Okay. So from here, there might be a kind of intuition that you may have that in ZP star, where P is a odd prime, the number of quadratic residue is, so if you have some intuition from here, then if I want to state if P is a odd prime, then the number of quadratic residues is how much, you guess, how much you want to say? If this could,
5p by 2.
how much? 5p by 2. Okay. So that is nothing but p minus 1 by 2 exactly. And here also you can see that the number would be same as p minus 1 by 2, the number of non-quadratic residues. So that is a kind of intuition that we may think of. And so this is one way of looking the whole thing, right? So this is the concept of quadratic residue and quadratic non-residue. Now you have some intuition about the term quadratic residue and quadratic non-residue. Okay, we can again think the same thing in a little different way. Okay, how? As I mentioned, suppose P is my odd prime. So ZP star is a cyclic group. You know the result. If P is prime, then ZP star is cyclic. Here we are taking little more extra, that is P is an odd prime. So suddenly ZP star is again a cyclic group. So I assume that G. Okay. Now tell me someone, what is any generator of Z11 star? Can anybody tell me any generator of Z11 star? Okay, let's have a for the sake of simplicity, let's take about Z7 star. Maybe that would be easier. Z7 star. Any generator of Z7 star? Can anybody please tell me? Z Orco propose, I think, yeah.
Six, in Z7. Yeah.
So any generator of Z7 star?
Z7 is the six generator.
6 generators.
I hope
Okay.
so.
How many generators are there for Z7 star?
So many.
5-7, sir.
5, 7.
Hmm.
Who is telling 5, 7? No, it's not 5, 7.
It could
Somebody,
be 5, 6.
why could be? It should be. It
I
must be.
guess it should be a 5,
So,
6.
so this, what is the order of this? Is 6, right? And we know that this is a cyclic group. So if this is a cyclic group, then it must be isomorphic to a group whose order is 6. So Z6 plus. Now if so asking the question how many generators are there here is same as asking the question how many generators are here. So how many generators are here? There are exactly phi of 6 many generators. And what is phi of 6? Is 2. So there exist exactly 2 generators of Z7 star. Now give me any one of them.
Sir, 5.
Okay. So 5 is a generator. Is 2 a generator?
No, sir.
Why not?
Sir, 2 can't give all the elements of set 6.
Okay.
Sir,
But you
GCD
said
of 2 and 6 is not equal to 1.
GCD of 2 and 6. So I am asking you to give a generator of Z7 star. Not. So see, so what you are actually mess up is I am asking you to give a generator for this, and somebody says 5 or somebody says 2. So the element, say for example, suppose 2, I am considering 2 here, and this 2 not same as this 2 here because they are isomorphic, right? So there must be some isomorphism here. Say phi is an isomorphism from say Z7 star to Z6. Now you have taken class 2. So what will be corresponding to class 2? Here this element will be the corresponding element of class 2 in Z6, right? So if suppose I am not sure whether 2 is a generator of Z7 star or not. Suppose I am not sure. Okay. Now you cannot directly discard this element that 2 is a generator of this or not, right? Now my question is, can you directly discard this? Suppose 2 here is a 2 is an element here, and you have a bijective mapping or an isomorphism phi. So phi inverse, you are considering phi inverse. Now corresponding to this class 2, whether the same class 2 will appear here or not, you are not sure basically, because the phi of class 2 may not be the class 2 here. So that way you cannot discard it, right? So you need to first understand what would be the isomorphism. That means which element goes where. Then only you can discard. Now somebody says that 5 is a generator of this. So that does not mean that here 5 will always reflect the class 5 here, because the class 5, where the class 5 of Z7 star goes, it depends on phi. So phi of class 5 will send the element of class 5 in Z7 star into some element of Z6 plus. Now if it will happen that class 5 goes to class 5 here also, then it is fine. Now you can understand, if class 5 could be a generator of here, after applying phi, which is an isomorphism, whatever will be the phi of class 5, that will also be a generator of Z6 star, Z6. And you know that in Z6 there is exactly two, either it should be class 1 or it should be class 5. Now you can check where it will go, right? Now if I ask you how many isomorphisms are there from Z7 star to Z6? Can anybody be able to answer me? How many how many isomorphisms are there from Z7 star to Z6 plus? Any answer to this question?
So 2.
Why?
So here we have two generators, and so the generators, I can map one generator to the generator of the other group for isomorphism. So there are only two
So
choices
this
for
is nothing
generators.
but the automorphism group. So yes. So it is nothing but the cardinality of automorphism group. So it's basically, this is also nothing but the cardinality of automorphism group. Isomorphisms are there from Z6 to Z6, right? So this is known as the cardinality of automorphism group. So that also forms a group, and that is known as automorphism group, and the cardinality of automorphism is nothing but phi of 6, and that is 2. Okay, so this kind of questions may be asked in the interview, in sometimes jam, or sometimes in competitive exams of different forms. They ask you this kind of questions. So this is quite important. Now it's clear to you, all of you. Is there any ambiguity or doubt? So who says that 5 is class 2 is not a generator? Now I think you understand that. So you cannot directly say, because it is not a generator here, but phi inverse of class 2 may not go to class 2. It may go to somewhere else. That's why you may not be able to directly say that class 2 is not a generator of Z7 star, but it may happen. Yes. Now is it clear to all of you?
So we can check the order of the elements. Order will be preserved. So if the
Yes,
order
order
of
will
2
be
in,
preserved.
but here 2 has order 3 in Z6, so it will also have order 3 in Z7 star.
Exactly.
So we
Yes.
can directly.
Yeah, that's true. Okay. So now say I need, so could anybody be able to give me any generator of Z11 star? Z11 star, then that will be easier. So I can continue with that example. Z11 star, can anybody be able to give me? So any generator of Z11 star? Okay, I will come to it. Try to find it. I'm sure you will get it. But why I am asking you this question, it has the reason is as follows. Okay, so just now I have told you that ZP star is a cyclic group, so it must be of this form. Sorry, it must be generated by some generator. Say G is a generator. So all elements of ZP star, you can suddenly write all elements of ZP star in terms of G. So the elements should look like this: G, G to the power 0, G to the power 1, G square, and so on till G to the power how much I should go? G to the power G to the power how much I should go? G to the power.
So P minus 1.
Okay, if it would be P minus 1, then how many elements are there here? How many elements are there?
Oh, sorry.
So,
P elements are there. So that will be P, 5 P minus 1 minus 1.
okay, so how much it should be? P minus
So 5 P minus, or sorry,
5.
P minus 2.
Yes, it should go till P minus 2. Now it's clear to all of you. It should not go till P minus 1, because if I put it P minus 1, then how many elements will be there? It starts with 0, and if it goes to P minus 1, then there will be P elements, but it has P minus 1 elements, right? So
So,
it can never be.
so
Yes,
2 is a generator of Z element star.
2 is a generator. Okay, that I will come to it later on. Just a minute. So why I need this generator, that will be clear for you very soon. Okay, so so every element of ZP star can be written uniquely in this form in terms of G. So all the elements can be represented in terms of this. So let me try to explain. Let me try to see the elements of Z11 star in that way. Okay, so here we have Z11 star. Then if 2 is, according to Pratik, if 2 is a generator, then suddenly it can be written as 1, because it's 2 to the power 0, 2, then 2 square means 4, then 2 cube means 8, then 2 to the power 4. What is that value, 2 to the power 4 in Z11? Can you
5.
please explain?
5.
5.
Sir.
Okay. Then 2 to the power 5 is how much?
10.
10. Then 2 to the power 6 is how much?
9.
9. 2 to the power 7 is how much?
7. 7.
18. Yes, 7. 2 to the power 8,
3.
14, and then 3. Yes, 2 to the power 9. 2 to the power 9 is 6, right? You just make it, multiplied it by 2, so 6. And 2 to the power 10, how much? 12
So
is 1, right? Now check whether all the elements are exhausted or not. Let's see. 1 is exhausted. Oh no, 2 to the power 10 is not 10. How much is 2 to the power 10? Is
So
it right? 2
1.
to the
Yes,
power
sir.
9 is how much?
So it will be 1. To the 10 is 1, sir.
2 to the power 10. So we should go till 2 to the power 9, right? It
Yes, sir.
has 11 elements. So we should not go because it's already a repetition. See, as I mentioned in my last one, it should go till 2 to the power p minus 2 and not p to the power. Now it will be clear to all of you, right? So we should go till p minus 2 and not p minus 1. That's why I again get back the same element 1. See, you can see here p is 11. So p minus 2 is 9. So we should go till is not here, because if we go till 2 to the power 10, then the same element 2 to the power 0 will appear. So it should be 2 to the power not up to this. Now we have 1 is exhausted, 2 is exhausted, 3 is exhausted, 4 is exhausted, 5 is exhausted, 6, 7, 8, 9, and 10. So all the elements. So you can see that all the elements are exhausted by using 2 and its powers. So Z11 star is a cyclic group which is generated by 2. So there is, we have already seen there is another, maybe the other generators also, but 2 is sufficient for us, one generator. Now just have a look at what are the quadratic residues. So here you see that the quadratic residues are 1, 4, 9, 5, 3. So 1, 4, 9, 5, 3. So just have a look at what are the elements. 1, 4, 9, 5, and 3. Right? So 1, I can write it in terms of 2 to the power 0. 4, I write so it looks like 6. Yeah, 2 to the power 0. 4 is 2 square. What is 9? 9 is how much? 2 to the power? 9 is 2 to the power 6. So it's 9, it's 2 to the power 6. 2 to the power 6. 5 is how much? 5 is 2 to the power 4. And 3 is how much? 3 is, where is 3? 3 is 2 to the power 8. Right? And what are the, so they are the quadratic residues. And let's see quadratic non-residues. Who are they? They are 2, 6, 7, 8, 10. 2, 6, 7, 8, 10. 2, 6, 7, 8, and 10. Let us have a look. 2 is 2 to the power 1. What is 6? 6 is here. 2 to the power 9. 7. What is 7? 7 is 2 to the power 7. What is 8? Something 2 to the power. 8 is 2 cube is 8. And what is 10? 10 is 2 to the power 5. Okay. Now, can you see in terms of powers some of the differences in case of quadratic residues and in case of quadratic non-residues? Can you observe something in terms of powers of the elements here? Any guess or any
So
idea?
even powers are quadratic residues.
Exactly. And what's about
So
quadratic
odd powers.
non-residues?
Odd powers.
So you can see it's not only the even powers, you can see that it's a kind of all even powers are in quadratic residues and all odd powers are in quadratic non-residues. On the other hand, if you take any quadratic non-residues, then its power must be odd, and if it is odd, then it has to be quadratic non-residue. Similarly here, if the power is even, then it has to be quadratic residue, and if it is a quadratic residue, then there its power must be even. Okay, so see there are two simple distinction in terms of the powers that also you can make if you write it in terms of a power of some generator. So that is also very interesting. The first interesting fact is the number of quadratic residues and the quadratic non-residues are exactly the same. Okay, so till now I haven't defined what is quadratic residue and what is quadratic non-residue in a very formal way, but intuitively what I want to give you an intuitive idea of what I am going to teach you formally, but before that you should have some intuitive idea. So here the intuitively the powers, if the number of quadratic residues and the quadratic non-residues, they should be the same in case of if you are considering it p to be an odd prime. And the second thing is that if you have, if you write this Zp star in terms of some generator and if you consider it as a power, then you see that all the powers which are of the form even number, then that corresponding number will give you quadratic residue, And if you consider the powers which are on the power of some generator, and if it is of the odd form, then it must be quadratic non-residues. So that is the whole thing that we are going to deal today, and you'll be very surprised to know that from this idea of quadratic residues and non-residues, and we'll little bit extend it. So here we talk only about a prime numbers, ZP odd prime. Then I will explain little bit more. Then that will deal with any integer, positive integer of course, which is greater than 2. That also give us an idea, and from there we'll actually get a very nice and very efficient algorithm to test whether a number is prime or not. So that is very important, and that's why quadratic reciprocity plays an important role. Okay, so now let us have a look at the formal definition of what is quadratic residues and what is not. Okay, so as I mentioned, I started with real numbers, and instead of real numbers, I can also give the same definition for ZP, or in particular for any abelian, finite abelian group. Okay, so this is the first definition, which is for modulo n, and it says that if n is a positive integer, we say that the integer a is a quadratic residue modulo n if and only if GCD of a and n is 1, and the congruence x square congruent to a mod n has a solution in the set of integers. Okay, just now I have mentioned about it's a definition in case of basically modulo n, or you can extend it in terms of Zn. Okay, so if n is a positive integer, see, whatever I give you the intuition, I talked about only prime numbers, but when I define it formally, it can be defined for any modulo n, okay, where n may be a prime or may not be a prime. But if a has to be a quadratic residue modulo n, the first thing is that GCD of a and n has to be 1. Okay, since I talked about only prime, so any integer which is strictly less than prime must be relatively prime. That's why in my definition, or in my intuitive idea of quadratic reciprocity, I did not talk about this GCD1 condition. But as you understand, for formalism, I required this. So this is the definition for any positive integer n, and a is a quadratic residue modulo n if and only if GCD of n equal to 1 and the congruence x square congruent to a modulo n has a solution in the set of integers. Okay, if the congruence x square congruent to a mod n has no solution in the set of integers, then we say a is a quadratic non-residue of n. Now it's clear. So since we are dealing with modulo n, we can suddenly consider this to be a class A, and we can consider this as an element of Zn star. So same definition could be extended or maybe defined in terms of Zn star. So if n is a positive integer, we say that a is a quadratic residue modulo n if and only if GCD of n equal to 1 and there is an equivalence class x in this Zn star such that class A is equal to class x star. So now you can talk about in terms of group. So this is class A. If there exists some element class x whose square is class A, then we call it A as a quadratic residue modulo n. Now this can also be further extended to any arbitrary abelian group. Of course, finite you can say. Not necessarily finite, so you can deal with any commutative group. So given a group G, an element A is a quadratic residue if there exists an element X such that x square equal to A. Okay, if I have this, then we call this X is a square root of A, and element is not a quadratic residue, is called quadratic non-residue. Clear? Okay, so in terms of group theory, it may not be required to have have the definition of quadratic residue or non-residue. One thing you should note that the definition is true for any group. Okay, so in case of any group, I can always define the quadratic residue or non-residue, but to get some more properties, I should have some extra property. Like for the definition of quadratic residue in terms of group, we may not require G to be abelian. But to have some more extra properties, I need something more. So here this is the proposition. What it says, in an abelian group, the set of all quadratic residues denoted by QR forms a subgroup of G. Okay, it's quite interesting. See here what we started with say Z11 star, right? So we know that Z11 star with respect to dot, it's a group, it's a commutative group, it's a finite group, it's a cyclic group. Many things we know. Now we have seen that quadratic residues. Who are the quadratic residues? So quadratic residues are 14953. 14953. So I'm omitting the class notation. So this should be class 1, class 4, class 9, class 5, and class 3. So this must be a subset of Z11 star, right? Now I am saying something more. So they are quadratic residues and this is quadratic non-residues, right? And it contains these elements 2, 6, 7, 8, and 10. Well, and they are quadratic residues. Now what this result says that if you have the group to be a abelian group, then the set of quadratic residues is a subgroup of that group. That means here this group, this subset is a subgroup of this. That means the set of all quadratic residues modulo something n here 11, or in case of any group which is abelian, then the set of all quadratic residues is a subgroup of that group. That's quite interesting. Now can anybody be able to give me any idea how to prove this? My statement is quite simple. My statement is, let G be a, where it is, oh, yeah, here it should be. Yeah. So in an abelian group, the set of all quadratic residues denoted by QR forms a subgroup of G. So suppose G is a abelian group and QR denote the set of all quadratic residues modulo quadratic residues. Here it's an arbitrary group, so you don't need to have some modulo. Suddenly, QR must be a subset of G, no doubt. Now, the first question is whether QR is non-empty or not. It may happen that QR is an empty subset of G. So there would be a problem for showing it to be a subgroup. So it has to be a non-empty. So how to show that QR is a non-empty subgroup of G? Any guess? Anybody?
So the identity element is a quadratic residue.
Exactly. So you can see that E square is always E, right? That's why E must be belongs to quadratic residue. That implies quadratic residue is non-empty. Very good. Then what I need to show? It's very easy. I need to take two elements, say A and B belongs to quadratic residue. To show what I need to show? I need to show A B inverse will also belongs to quadratic residue, right? So how to show that? Since A and B are in quadratic residues, so there must exist some x and y such that, what can I write about x and y and A and B? Such that A must be of
Excess.
x squared and
Excess.
B must be some y squared, right? Now what I need? A B inverse, right? So this is nothing but x squared into y square inverse. Now you understand why I require the abelian group property. Unless you have this abelian property, you cannot write like this x y inverse whole square. By using abelian property or the commutativity of the group G, you can suddenly write this as this. So this is nothing but a square of some element. So AB inverse is nothing but a square of some element, because x and y, x y inverse, so that is an element of G. X y inverse belongs to G. So AB inverse, for AB inverse, there exists x y inverse such that if you make x y inverse whole square, then that is equal to AB inverse. That means AB inverse has a square root. That means AB inverse belongs to quadratic residues. As a result, as I as I claimed that AB inverse belongs to QR. As a result, QR is a subgroup of G. Is it clear? Is the proof clear to all of you?
Yes, sir.
Good. So the first result is clear. As a result, you can now say that this is a subgroup of Z11 star. So now we are basically in algebra. So now you can understand that the groups, the quadratic residues, it forms a subgroup of the original group. So it will have lots of property. Now if I ask you the question, is QNR the set of all quadratic non-residues? Will that be also a subgroup of quadratic G? What is your opinion?
No, sir. 2 is a quadratic non-residue, but 2 square is quadratic residue. So it will not be a subgroup.
Not a subgroup. You can, yes, that's a very good answer, but you can certainly say that identity element can never be in QNR. So it can never be a subgroup, because to be a subgroup, it should have the identity element, but identity element can never be within QNR. So it cannot be, and your result is also it cannot hold the this your closure property will not be satisfied here. So that's good. So it's clear to all of you. Okay. Now the question is, how do I check for a group for Z11 star? I have exhausted all the elements, but if I ask you the same question in terms of say Z, if I give you say for example 99, and if I ask you the question whether 99 is a quadratic residue in Z101 star, one way could be you explore all the elements, 100 elements, and check whether 99 has square root or not. Okay, but that could be a tedious job. It could be maybe a bigger. So 101 is a prime integer, so all my previous results hold. So you understand that 99 may be a quadratic residue and may not be a quadratic residue. So you directly, till now whatever I teach you, you may not have any idea how to check whether 99 is a quadratic residue or not, except for the fact that you can exhaust all the quadratic residues, and from there you can guess whether it belongs to or does not belong to. Okay, but there might be some efficient way to do that. So let us try to explore few of them. To understand that, let us have few further uh, techniques. Okay. So I have already mentioned you about 11 Z11 star, and I have already mentioned you that if few more important results. Okay, one thing you see here, and when I started, if the quadratic residue exists, for example, if 1 is a quadratic residue modulo 11. So if I ask you the question exactly how many square roots are there, the answer is exactly 2. So 1 and 10 are the square roots. For 4, 2 and 9 are the square roots. For 9, exactly 2. So if you consider any element, for example, from ZP star, two cases may happen. Either it may be a quadratic residue or it may not be a quadratic may not be a quadratic residue. So if it is a quadratic residue, then suddenly it will have exactly two square roots, right? So that's again a very important observation. Okay, so here it states that let P be an odd prime and A be an integer such that GCD of AP equal to 1. Then the congruence x square congruent to A mod P has either no solution or exactly two incongruent solutions modulo P. What does it mean, incongruent solution? Incongruent solution means, so here we see that it has exactly two solutions, and 1 and 10 they are not congruent, but 1 and 12 they are congruent. But what it says, if it has a solution, then it will have exactly two solutions, and these two solutions will be incongruent solution. Now you can see that it will have exactly infinitely many solutions. For example, x square congruent to 1. So this has infinitely many solutions, because you can understand that in integer, you can understand that if I put it 1, then if I put it 13, that not 13, 12, then that will also be a solution, because class 1 and class 12 are same in Z11 star. Okay. As a result, what it happens, as a result, you can say that there exists infinitely many solutions, but they are congruent. But the result says that if it has a solution, that means if that is a quadratic residue, then it should have exactly two incongruent solutions. So here exactly two solutions, and these two solutions are not congruent. So that is the result. Now you can very easily check this, how to prove this. So from your maybe from your 12 level or from your first year level, you have already seen this kind of technique. If I want to prove either this hold or this hold, then what you start with one and then prove it, and then automatically the other things will hold, right? So what I need, either no solution or exactly two incongruent solutions modulo P. So what the proof technique would be, start with it has a solution, then if you able to prove this, then it will automatically prove that it will either have no solution or has exactly two solutions which are incongruent. Okay, so that's why I have started with the argument that let the congruence this have a solution in Z. So what will be our target? We'll show that there will be exactly two solutions, and these two solutions are incongruent solutions. Okay, so let us start with this. Suppose this is a solution, say y1, then I must have y1 square equal to a modulo p, because this is a solution. This implies minus 1 square is also, because this is also y1 square, so you can always write y1 as minus y1 square, which implies that minus y1 is also a solution congruent to in the congruence this. Now what we need to show that, we need to show that y1 and minus y1 are two incongruent solutions modulo p. So here if you look at 1 and this is 10, what is the relation between 1 and 10? So class 1, and if I consider minus of class 1, what is minus of class 1 in Z11 star? That is nothing but class 10. So the same thing happens here. The proof is exactly the same. So 1 is a solution, minus 1 is also a solution. What is minus 1? Minus 1 is nothing but 10. So that's why here is the result. This, which implies that minus y is also a solution of the congruence this. Now we shall show that y1 and minus y1 are incongruent modulo p. Now here we need to emphasize this, we have taken odd prime. So there is one case remains regarding prime, that is the even prime. And we know that 2 is the only even prime, so we exclude that part. Now you understand why we have excluded that part. So if you now check why they are incongruent. So on the contrary, suppose we assume that they are congruent, that is y1 is congruent to minus y1 modulo p. So that means 2 of y1 modulo p. So that means p divides 2 of y1. Now since p is an odd prime, so p cannot divide 2. So p must divide y1. Okay. This shows that p divides y1. So if p divides y1, then y1 square must be equal to 0 mod p. I mean, it's quite clear. So that means y1 congruent to 0 mod p. That means y1 square is also congruent to 0 mod p. Also, from hypothesis, you have already given that y1 square equal to a mod p. So from these two, what will be your conclusion? A must be 0 mod p. That is, p must divide a. But see, you have already taken this condition, GCD of AP equal to 1. That cannot happen because if GCD of AP equal to 1, then suddenly P cannot divide 1, A. So it's a contradiction. And why this contradiction happens? Because we have assumed that they are not incongruent. Y1 and Y minus Y1 are not incongruent. So that was the reason why we get the contradiction. So what would be your idea? Your idea would be they are incongruent. Okay. And see, so this is the quite very popular technique to use the method of contradiction. And as I mentioned in my very earlier classes of number theory, that this contradiction method was firstly written in a book, was given by who is that guy who actually gave the for the first time in the history of mathematics in a written form was Gauss. Sorry, not Gauss, Euclid. So Euclid was the guy. So he was around 3,000 years back. He actually devised the idea how to get something using method of contradiction. So Euclid was the first guy who gave that concept to show that there exist infinitely many primes. So it's quite amazing. And till now, the GCD algorithm given by Euclid was considered to be the one of the most efficient algorithm in finding GCD, greatest common divisor of two positive integers. So it's amazing guy was there. So now till now we have already proved that there exist two incongruent solutions, and now we'll have to show that there exists no other solution. Then only we'll able to prove that exactly. So we have proved that two solutions are there. That means there may be more solutions, but now we will give some argument which will help us to justify that there exist exactly two solutions and they are incongruent. Okay. Okay. So there exist two incongruent solutions. Okay. So now we shall prove that there exist exactly two incongruent solutions modulo p. Okay. Suppose there exist more. That means let Z be any solution of this. Okay, now let us try to prove in that way that take any solutions of this, and if I can able to show that either Z is congruent to y1 or Z is congruent to y2 minus y1, then we are done basically. What I am taking, the logic is like this, I need to show exactly two, right? So I take any solution of x square modulo p, and by some argument I will try to show that this Z is either congruent to y1 or this Z is congruent to minus y1. That means if you take any solution, then this solution must be of either y1 or minus y1. Then that will in turn prove you that there exist exactly two solutions. How to prove that? So Z is any solution, that means this holds. Now again it was solution we have already seen, that means y1 square. So by from this two, what will be your conclusion? Y1 square congruent to Z square modulo p, which implies that if I make a side change, then y1 square minus z1 square is congruent to 0 mod p. That means p divides y1 square minus z1 z square. So in turn it will p divides this. Now remember p is a prime. So that means either p divides this or p divides this. Now if P divides this, then you will have what? Y. So Z is congruent to, if you consider this, then what would be this? So this means P divides Y1 plus Z. So P divides Y1 plus Z, P divides Y1 plus Z. That means Y1 plus Z is congruent to 0 mod P, which in turn will reply Z is congruent to minus Y1 mod P. Similarly, if you have P divides Y1 minus Z, that imply, sorry, this normal Z, Z is congruent to Y mod P. So what you Y1 mod P. So what you have shown, you have taken any solution of this, you have shown that either Z is congruent to this or Z is congruent to this. So you have done basically. So is the result clear to all of you? Any question or doubt? Any question that anybody has? Is it clear to all of you? Okay. So I assume that it's clear to all of you. It's quite easy. It's nothing. So as an argument or as a corollary, you can say that if P is an odd prime, then the congruence x square congruent to, so instead of A, I put it 1, modulo P has exactly two incongruent solution. Now you can understand 1 and minus 1 are the exactly two solutions of this congruence. So that's very easy. Okay. Now what I need to show is now is that the number of how many elements are there which are quadratic residues and how many elements are there which are quadratic non-residues. So we have already seen, intuitively we have already guessed this value should be like this. Now I need to prove what are this. So again I first give to a kind of intuitive proof. So let us try to make a function, say phi is a function from Z11 star to say Z11 star. Define y, phi of any element, any x goes to x square. Okay, for all x belongs to Z11 star. Okay, now is it a function? Surely it's a function. Now if you do that, what is your observation? So here you have all 1 to up to 10, but here it's going to a particular set, right? So this is also Z11 star and this is also Z11 star, but suddenly it goes to not everywhere. Where it will go? It will go this set. What will be this set? Can anybody say what will be this set?
So quadratic residues.
So this is nothing but the quadratic residue, because this is going to all the square elements of this. That means whose square root exist, right? So what are they? We have already checked. What are these elements? Let me check. So they are 14953. So 14953. So that goes to where it is. Okay, it has gone somewhere. Yeah. Okay, it may be somewhere. Let me start again. So Z11 star to Z11 star, define y, phi of, so I'm defining a phi of class x goes to class x square. And so if I have all the elements 10, but we can see that it goes to 1. What was there? 1, 4, 1, 1. What are the quadratic residue? Can somebody tell me? 1, 1,
4, 9, 5, and 3.
1, 4, 9, 5, and 3. Okay. So now using that function, Is it, can you tell me that the set of quadratic residue is exactly half of the order of this? Now can you tell me that somebody using this function, the quadratic residue set is nothing but ZP star by 2? Any guess, any idea? So that's the, I have given the proof actually, but with an example, but that's the proof. Anybody?
So this will be a homomorphism as phi xy class is sent to x square y square class. So it is a homomorphism from Z11 star to Z11 star, and
Yes,
the kernel is the pre-image of 1, which has cardinality 2, as we have seen from the previous corollary.
yes,
So Z11 star mod card phi is homomorphic to the image of this Z, the quadratic residue set. So it will
yes,
be half.
it will be half. Uh, yes, so is it clear to all of you? Now, how will you show that? So, could you please repeat once again? I think many, is it clear to all of you? Or shall he repeat? Shall he repeat sometime? Or is it clear to all of you? Okay, what he tells like this, so phi is a homomorphism. Is it clear? Is a homomorphism. First, try to prove this. What do we need to check? Phi of some element. I am dropping the class notation xy. What is this value? This is, sorry, this is xy whole square. And since this is a commutative group, so you can write xy. Other way, this is also fine. So this is, sorry, this is, sorry, not xy. So I should write x square y square. This is a commutative group. So this is phi x, phi y. So this is a group homomorphism, right? Okay. Now then what? Then what is the kernel? So if you have a group homomorphism, then you must have a kernel. So what is that kernel? Let us try to find. So yes. So kernel of phi. What is that kernel of phi? Can anybody be able to say? So that means all such element, whose element x. So I'm just putting x, not all such element x belongs to Z11 star such that phi of x equal to the identity element of the right side. So that is 1. That means class 1. That means all such x belongs to Z11 star such that phi of x means x square equal to 1. Just now we have seen that for x square congruent to 1 mod p, it has exactly two solutions. That means it should be plus and minus 1. So they are all classes, right? I'm just dropping the class notation. That means cardinality is this. Okay. Now what is his second or third observation? What is his third observation? Can anybody repeat?
So isomorphism theorem.
Okay. So by
First
first
isomorphism.
isomorphism theorem, so Z11 star quotient kernel of phi, that must be isomorphic to who? Which group?
Quadratic residue set.
Why? How will you say that this is quadratic
So,
residue set?
so this is the
So
image of the
yes.
function.
So image, it should be like image of phi. Now you need to show what is that image of phi. Now you can understand what is image of phi. If from the image is quite clear, the image actually goes to the QR, right? So that is only the image. That means this is nothing but quadratic residue. Okay. So what is the cardinality of then quadratic residue? The cardinality of quadratic residue is, since this is a finite group, then only I can do this by kernel. I have just seen it's 2. So this is p minus 1 by 2. Is it clear to all of you?
Yes, sir.
Good. So in the book, the same thing is, I tell the same thing, but since in the book you cannot write it in a very detailed way, so you can see that this is a 2 to 1 function. So that actually gives you this idea. So every 2 element goes to a single element, and that gives you the idea of this proof. So as I have mentioned that if element is either quadratic residue or quadratic non-residue, that means here you have quadratic non-residue, this is quadratic residue, this is quadratic non-residue. If this size is mod z p star by 2, then suddenly the size of quadratic residues, non-residues will also be the same, z p star by 2. That means the number of quadratic residues and quadratic non-residues are exactly the same. Clear? So that's where we have started. But intuitively, now you have the formal proof of the same result. So it's always good to have the informal idea, especially in case of number theory. It's good to have an informal idea. If you have this informal idea, then try to develop the theorem. If I start with this theorem very formally, then it may be difficult for you to grasp it. But now, since I have started from a very basic thing and very example way, it's now easy. The statement is quite clear. So what I feel that if you understand the statement of the theorem, then it's very easy to follow the proofs. Most of the cases, not always, but most of the cases, if you understand the proof technique by some example, then it's very easy for you to follow the proof. That's why I started with example, and usually I do it like this. I first start with example, first give you the idea of how the example works, and when you understand how the example works, then the formalism is easy. It's not always the case, but for especially for the number theory, basic number theory, this idea could be useful. Okay. Now again I come to this question that I have already asked you, that what could be, whether if I start with this, I think I lost it maybe, okay, some places somewhere. The question was, in if I ask you whether 99 is a question is 99 a quadratic residue modulo 101? This is my question. Till now, whatever we understand or we know a little bit about quadratic residues, non-residues, etc., but to give the answer, till now we don't have much tools at our hand. So what to do? So to solve this problem, it was actually a question, and to solve this problem, few notations have been used. Okay, so that I'm going to explain. I'm just erasing all of them. Yes. And that is known as Ligendre symbol. Ligendre metis, Ligendre symbol. So let me here, yes. So this is known as Ligendre symbol. Okay, so explain. Ligendre symbol. So theoretically, what does it mean? It says that suppose this notation is denoted by this. So I am talking about, say, for example, P. It could be in, I will see it later on when the name will be changed to Jacobi symbol. But for the time being, for Ligendre symbol, P is nothing but a prime. And most of our cases, it has to be an odd prime. And GCD of AP equal to 1. So here, GCD of AP equal to 1, and P is an odd prime, suppose. Now, what is the meaning of this? This value is either 1 or -1 depending on the cases. AP, this value, Legendre symbol AP is 1 if A is a quadratic residue modulo P, and -1 if A is a quadratic non-residue modulo P. Some of the books, they have also given some extra term 0. In that case, they don't consider this. So they put AP value equal to 0 if P divides A. That means in that case, A and P, they are not relatively prime. So they consider this, but in my book and in many books, they don't consider this case where P divides A. So to avoid that case, we have assumed that GCD of AP equal to 1. Okay. So in our definition, we don't have this 0. Clear? Okay. So if I again ask you the question, what is, so now I can formulate the value, the question that whether 99 was a quadratic residue modulo P or not. That means in terms of Legendre symbol, my question is 99, 101, what is his value? Is it 1 or -1? If this value is 1, then you can say that it's a quadratic residue. If this value is -1, you say that this is not a quadratic residue. Okay, so that is our goal to find of this value. But till now, we are not in a position to calculate its value. We have just started a journey towards it by using the term or by defining the term Legendre symbol. Okay, so let us try to have what is this value. So we need to have some formula or some technique to calculate this value. Okay, so that's the idea. So in case of my previous example, if you see that, so A11, this value is 1 for 1, 3, 4, 5, 9, and -1 for 2, 6, 7, 8, and 10. Okay. So let us try to see how these values could be generated. In my initially, I have already mentioned that we consider, since P is a odd prime, so we consider ZP star. And for ZP star, we understand that this is a finite group, this is a commutative group. Not only that, this is a cyclic group of order P-1. That part we already know. So we assume that ZP star is generated by some generator G. So we can always write G in terms of like this. Okay. See here we went up to P-2. Now this observation is very important. G to the power I is equal to G to the power I modulo P-1. See, this is very important, and for many competitive exams, this formula gives you a lot of hints for solving this problem. In terms of cyclic group related problems which are multiplicative in nature. So G to the power I is same as G to the power I modulo P-1. Okay. So if I have this set as my ZP star. So ZP star I can always write in this way in terms of G. Now what I do, I just make every element a square. Okay. So this is a set which is nothing but ZP star. Now from that set, I just construct a new set by squaring every element of the set. Now the question is, how many elements that do we have? So here we have G to the power 0 will become G to the power 0 itself. G1 will be G squared, G to the power 4, and so on. But after some time, you will suddenly use this property you will find that after some time, after G to the power P-3, it will again repeat. Okay. So why it is repeating? Because it's basically a 2 to 1 mapping. So every two elements will go to a single element because you are basically squaring every element of this set. So this contains a list of all quadratic residue modulo P. Note that in the multiset, because why do we call it multiset? Because in a set theoretic notation, no element can be repeated, right? So you cannot say this as a set like 1, 2, 2, 3. We don't call it as a set. To have set in theoretic notation, it should be 1, 2, and 3, and not 1, 2 to 3. So to define this kind of set, we sometimes call it multi-set. Multi-set, which may in this set, same element may repeat. Okay, so that's why I mentioned it. This is a multi-set because if you square all the elements, then you will have G0 twice, G squared twice, and so on. So this contains the list of all quadratic residues in GetP star. Note that in the multiset, each quadratic residue appears exactly twice. Thus, quadratic residue, so this is the QRP, means quadratic residue modulo P is nothing but this set. So we see that the quadratic residue ZP star are exactly those elements that can be written as g to the power I with I equal to 0, this an even integer. This leads to the following result. I have already explained you in terms of the example. So g to the power n is a quadratic residue if n is even, and g to the power n is a quadratic non-residue if n is odd. That part is clear to all of you now, I am sure. So depending on the n, you can say that whether this is a quadratic residue or this is quadratic non-residue. So this result will be helpful for the finding some values of the Legendre symbol. So now I will give you a formula for Legendre symbol. Till now I had no idea about how to calculate 99101, right? Only the if 99 is a quadratic residue, I know its value will be 1. If 99 will be a quadratic non-residue, then its value will be -1. But till now we had no clue how to calculate this value. So now we are in a position to show you how to calculate this value. Okay, this is quite interesting. So this is the formula. So let P be an odd prime and A be an integer such that GCD of AP equal to 1. That means, as I mentioned, to have the Legendre symbol, GCD of AP has to be 1 and P has to be an odd prime. That's for definition. So it says that its formula is, this is congruent to A to the power P minus 1 by 2 modulo P. That means if this is a correct answer or correct formula, then 9901, this value should be A to the power P minus 1. That means 101 minus 1 by 2 modulo 101. That means modulo P means modulo 101. So that means you need to calculate, basically this is nothing but 99 to the power 50 modulo 101. So can you very quickly tell me what is this value, whether this is 1 or -1? Anybody? Any quick answer? Suppose I assume that this formula is correct. Then can you tell me very quickly what would be its value, whether this is quadratic residue or quadratic non-residue? Well, it's difficult till now, right? So I have a formula, but as I mentioned, it's really not very easy for you to calculate till. So I need something more. But before going that, let us have a look at the formula first. And then I try to first I will prove this formula. Okay.
It is 1.
How did you calculate it?
So 99 is congruent to -2 mod 101.
Yes.
So it will be congruent to 2 to the power 50.
Yes.
And 2 to the power 5 is congruent to -1.
Yes.
So it is 2 to the
2
power
to the
5.
power 5 is congruent to?
Sorry,
101, not
sorry,
in
yes,
100.
yes, sir.
Yes.
Sorry, sir.
Yeah. So it would be difficult. But till now, whatever I teach you is not very easy for you to calculate. So it's a straightforward. You need to find this value, but in modulo 101, not in 100. If it would be in 100, then it would be easier for you to calculate, but it's in 101. Okay, so first I go for the formal proof of this theorem, then I will go for few extra formulae, and from that formulae it would be easier for you to calculate. So don't worry about this, but first try to grasp what is the formula, whether this formula is correct or not. Okay, so what I need to check, I need to check that if AP, this Legendre symbol value, is congruent to this value. Okay, now two things may happen. AP, this value is either 1 or -1. That's by definition. So let A be a quadratic residue modulo P. Okay, so two things may happen. So A is just an positive integer. So two things happen. Either A is quadratic residue or A is not a quadratic residue. If A is a quadratic residue modulo P, then we know that this value has to be 1. Okay. Now let G be a generator of ZP star. Okay. Then by this, as A is a quadratic residue, what I mentioned, if this is a quadratic residue, then when I represent A in terms of G, the generator, the power must be an even integer since it's a quadratic residue. So G A class A equal to G to the power 2 to the power I, where I is some integer. That means here the power has to be even. Thus, A to the power P minus 1, the right hand side. If I consider it in terms of G, then what I write? In place of A, I just put it G to the power 2 to the power I, because class A is nothing but G to the power 2I to the power this. So ultimately G to the power P minus 1 to the power I. So what is G to the power P minus 1? Is by Fermat's little theorem. This value is 1. So ultimately this becomes 1 by Fermat's little theorem. So AP is congruent to 1 modulo P, because A is a quadratic residue, and from the right hand side I have also seen that that is also 1 modulo P. So this value. So Legendre symbol AP is congruent to A to the power P minus 1 modulo P. Is the proof clear to all of you? So is the proof clear to all of you? Any doubt or question? Then I can write if you want. Shall I write or is it clear? Okay. So I assume that that is right? Okay. So you understand. Now the other case. So we have already assumed that A was a quadratic residue. So other case must be A is a quadratic non-residue. Okay. If this is A is a quadratic non-residue, then in terms of G, the power must be an odd power. So 2 to the power I plus 1. Then again the same thing, A to the power P minus 1 by 2 should be equal to, I put this value, and that becomes this. So I make it in a different way. And then if I do like this, if I do a little bit of calculation, jugglery of this here and there, then you will find ultimately G to the power P minus 1 by 2 modulo P. Okay. Now, what I need to show actually, I need to show that this value should be minus 1 modulo P, right? So I need to somehow show that this value is minus 1 modulo P. Now, if I make a square of this value, that becomes 1 by Fermat's little theorem. So this value square is 1. That means if I consider this, if I consider this square root, then this square root value will be either plus 1 or minus 1. Just we have shown that x square congruent to 1 modulo P, it has exactly two solutions, either 1 or minus 1. So here also, if I consider g to the power P minus 1 congruent to 1 mod P, so you can write it in this way, g to the power P minus 1 by 2 whole square congruent to 1 mod P. So what will be your conclusion? This square root will have exactly two solutions. So either g to the power P minus 1 by 2 is congruent to 1 mod P or minus 1 mod P. Now can somebody tell me this case will not happen. Why? Can somebody tell me why this will not
So,
happen?
so order
Yes,
of G is P minus 1.
exactly. So see, G is a generator of which group? G is the generator of this group. So what is the order of this element G? It has to be the order of the group. That means P minus 1. If this is 1, then what will be your conclusion? The order will certainly be less than P minus 1. But that cannot be the case because G is a generator. Its order must be P minus 1, and you cannot have G to the power something which is strictly less than P minus 1, and that gives you the value of 1 unless it's 0. So it's not a 0. P minus 1 by 2 is not a 0. So it has to be minus 1. You cannot have this value to be 1. If this value to be 1, then the order of G must be strictly less than P minus 1, which is not the case, which will get a contradiction. So this value has to be minus 1 modulo P. So you started with A to be quadratic non-residue. That's why the Legendre symbol value was minus 1. And on the other hand, you have just proved that A to the power P minus 1 by 2 is also minus 1 modulo P. So they are congruent. Is it clear to you? Any question or doubt? If you have, please don't hesitate. Any question till now you have? Okay, so I assume that you understood the uh, proof. The proof is really easy, it's not very difficult. But the thing that I'm going to give you is very important now. That will help you to give the answer of my question 99 modulo 101, whether is that's a quadratic residue or not. Here there are few important properties. First property is Legendre symbol ABP equal to Legendre symbol AP into BP. These proofs are very easy, follows from the definition. So what is this proof? You can see that this proof is very easy. Why? If you consider this, if you consider ABP, so ABP where we assume that GCD of ABP equal to 1, then this value from definition, this is nothing but AB to the power P minus 1 by 2 modulo P. Just now we have proved this theorem, and since this is a commutative group, you can write it like this: P minus 1 by 2 mod P into B to the power P minus 1 by 2 mod P. And this is nothing but AP and BP. See, one thing you just need to prove that I have proved it in terms of modulo P, right? But here I have written in this way, I have written equal to. How this equality happens? That's a, its value is either 1 or minus 1. You have few cases, then from there you will resolve that they are exactly equal. And but till now what I have proved, they are equal in terms of modulo P. But from there you can very easily, since these values are either 1 or minus 1, Legendre symbols values are either 1 or minus 1, you can very easily prove that they are actually equal. Okay. Now if you consider this is again a important result. If you have A congruent to B mod P, implies A modulo AP equal to BP. That means if I consider what is this result, if say in J11 star I am considering, we understand that class 2 is equal to class 13, right? Okay, so what is this value? 211 and 1311. It says that if, since 2 is congruent to 13 modulo 11, so you can replace this by this, the same thing. That means you can have the value are exactly the same. That proof is also very easy. You can prove it. Again, the equality will be little just extra 2 or 3 steps that will give you the exact equality. Okay. So this is very helpful result, and that will be very helpful in for your calculating the values properly. The third result, it says that a square p, that is again very interesting. If you have some square of some number, then that value is always 1. Why this is 1? You can understand that a square p, the proof is very simple, equal to a to the a square to the power p minus 1 by 2 modulo p, and that value becomes, this is congruent, a to the power p minus 1 modulo p, and by Fermat's little theorem that is 1. Okay, but this is very important result, and it gives you lots of extra facility, efficiency in calculating things. And then 1p is 1 and minus 1p is nothing but the same thing, minus 1 to the power p minus 1 by 2 and so on. Okay. Now if I ask you the question, what happens for 99? Now you need to calculate, what you calculate is 99101, right? And this is nothing but, you can break it down like this: 3 square 11 into 11, sorry, 101 101, right? You can break it by using this formula. Now what to do? This value, what is this value? This is square, so this is 1. That's why this is 11101. Now you need to calculate. So 99 Ligendre symbol 101 simply becomes 11101. Okay. Now you need to calculate what? 11 to the power 50 modulo 101. If you are able to calculate this, then you are done basically. So again the question is how to calculate 11 to the power 50 modulo 101. Again you will be little stuck, or you can do this, but you will be little stuck here. So I need to have some more formulae, and that is known as Gauss formula. I will do it, maybe it will be your turn to read it, but I will come to here. Law of quadratic reciprocity, or maybe I will do it in my next class, I will explain it, but I will go to another formulae which will help you to get this value. Yes, this is important. So this is known as law of quadratic reciprocity, and that gives you a very nice way to calculate the Ligendre symbol very efficiently. What it says? It says that if P and Q are two distinct odd primes, then this product PQ Ligendre symbol and QP, that is same as minus 1 to the power P minus 1 by 2 into Q minus 1 by 2. That's very easy now. And that can be represented in a better way, maybe in this way. The proof, I will come to this proof in few days. So in my 2 or 3 classes, I will be doing only with this quadratic reciprocities, and that will give you a idea, basic idea. But this, from the same result, it says that PQ is same as QP if any one of them, P is either congruent to 1 mod 4 or Q is congruent to 1 mod 4. If any of the P or Q are of the form 1 mod 4, then if I just replace reciprocal like concept, if I have, these values will be same. But if both of them are of the form 3 mod 4, if both P and Q are of the form 3 mod 4, then this value will be just minus of the opposite of this. Okay. Now with this result, this is known as law of quadratic reciprocity. Now the idea is clear, I guess. If any one of the PQs are of this form 1 mod 4 or Q is of the form 1 mod 4, then PQ and QP, these values are the same. But if both of them are of the form 3 mod 4, you can see that all of the cases are exhausted here. You will find no other cases with mod 4. So if both of them are of the form 3 mod 4, then the value will be just the negative of the others. Now can you tell me what would be this value? See, this is 101. This is 101 is congruent to 1 mod 4. That means I have already one of them, P and Q, are of this form. Those that means I can replace it. What is my advantage for this? Now what can I say about this? What is this value? Now you can see 101 is congruent to how much modulo 11? Can anybody say very quickly?
So 2.
Very good. So this is 2. So I can replace by this formula. You have already seen this formula. This formula you have already seen. This formula. If A is congruent to B, that means you can replace A by B. These values are same. So since this is congruent to 2, so I can replace it by 211. Now can anybody say what is this value? So that means 2 to the power 11. So now 5 modulo 11. Now it's very easy. Tell me quickly, what is this value?
9, sir.
9.
So minus 10. Minus.
So,
Yes, 10, sir. 10.
so 10 means modulo 11. That means minus 1 modulo 11. That means this value is minus 1. That means 99 is a quadratic non-residue modulo 101. Clear? So these formulae are very useful in constructing. Now you can very easily have these values. So very quickly, can you just give me the answer for what would be the value for, say anything, maybe 96 modulo 101? Quickly. So it will be your test. How